Hello everyone. As you may have heard, seismic measurements of Mars have indicated that there is a subsurface water reservoir between 11.5 and 20 kilometers deep. This was hinted at before when a Mars orbiter detected anomalies in its magnetic field, indicating that there was a brine reservoir deep in the crust. The surface of Mars is incredibly arid and desolate, and may very well be completely inhospitable to life. So, Martian microbes could have found a refuge deep underground. But contrary to popular belief, not all liquid water can support life. One example is the Dalal pools in Ethiopia, which are 50% salts by weight and have a pH of 0. While microbes which can tolerate either the salinity or acidity present in the pools have been found, it's likely the combination of the two renders them uninhabitable. Another place is the water not around, in deep-sea hydrothermal vents. As the pressure increases, so does the boiling point of water, and the immense weight of the ocean above it allows water in the vent column to stay liquid at 350 degrees Celsius, or 623 degrees Kelvin. So, liquid water doesn't guarantee the presence of life. We can be fairly certain that the water deep in the Martian crust is briny, but it's impossible to get a good idea of its pH, so we can't say whether or not it's chemically suitable for life at this point. But what about its physical characteristics? Well, as you go down on Earth's crust, the temperature will increase until you get to a point where the rock melts, and the geothermal gradient here is roughly 25 degrees per kilometer. On Mars, the geothermal gradient is believed to be between 10.6 and 6.4 degrees per kilometer. The average surface temperature of Mars is 210 degrees Kelvin, so if it's 10.6 degrees per kilometer, the temperature at the top of the reservoir would be 332 degrees Kelvin, and at the base it'd be 422. Water boils at 373 degrees Kelvin, and even if the pressures can keep water liquid at those temperatures, most organisms can't survive, let alone metabolize, in these conditions. Although, we have found a few which can grow above the boiling point, with one taxa being able to do so at 394 degrees Kelvin. So, if the high estimate for the geothermal gradient is correct, most organisms could only live in the top 3.9 kilometers of the reservoir, while the hardier ones could survive at a depth 2 kilometers lower. But, if the lower estimate for the geothermal gradient is correct, the top of the reservoir would be 284 degrees Kelvin, or just 11 degrees Celsius, and the base would be 338 Kelvin, or 65 degrees Celsius, i.e. the entire reservoir would be habitable. If microorganisms are indeed in the deep crust, they could react hydrogen coming up from the mantle with carbon dioxide percolating in from the atmosphere to produce methane. We have observed methane being released from a subsurface reservoir, and it may very well be being produced by microbes in the deep crust. There are also trace amounts of oxygen in the Martian atmosphere, and this could be used by subsurface organisms to oxidize not only hydrogen, but ferrous iron and hydrogen sulfide as an energy source. So, while the Martian surface may be too harsh for anything to survive, or at least metabolize and grow, life could still thrive tucked away deep in the crust.